Right. Let me just conclude this chapter here on differential equations using operator D by solving this differential equation. Solve. Sorry. Solve. Solve. What? What is it that we want to solve? D to the power 4 of y plus 2d cubed y plus d squared y is equals to 4e to the power x. Can you hear me? Right. We solve that. First thing, we form an Ox equation. What is our Ox equation? Our Ox equation is the M equation. Our M equation is m to the power 4 plus 2m cubed plus m squared equal to 0. That is our Ox equation. Then out of that, we solve that equation. Solving that equation, there's m to the power 4, m cubed, m squared. So m squared is the common factor. Then we left the m squared here, plus what? Plus 2m plus 1 equal to 0. That is m squared is equal to 0, or m factors here, m plus 1 all squared equal to 0. That is here. Here, m is 0. I hope you'll recall here twice. Or again here, m plus 1 is equal to 0. When you take the square root of 0, that is m is equal to what? Is equals to minus 1. Again here, what? Twice. Because it's m plus 1 into m plus 1. What is then the solution? So your y from this m equal to 0 twice here is what? Is a to the power 0x twice plus b x a to the power 0x. And solution for that one, or what? Y is equals to minus 1. But now I've used a, I've used b. Then the next one is c. Perhaps I don't use c because c perhaps might confuse us with the constant of integration. Then d might also confuse us with the operator d. Then I pick up e. So it's a to the power small a to the power minus x twice is what? Is f what? X a to the power minus x. If I combine these two, combine so as to give me YCF, that will give us, that will be a plus what? Plus bx plus a small a to the power minus x plus fx a to the power minus x. That is your y complementary function. Are we there? Then solve for y from the original equation. Then your y pi is equals to 1 all over d to the power 4 plus 2d cubed plus what? Plus d squared. The action, I remember very well, the action is on what? Is on 4 e to the power x. Now, you know how to enter that now. Which theorem are we going to use here? It's theorem 1. perhaps by theorem 1, because this is exponential. So we use theorem 1. Yeah. By theorem 1, which is exponential. By theorem 1, e to the power x in front, that's 1, all over what? 1 to the power 4, coefficient that's 1, plus what? Plus 2 times 1, plus what? 1 squared. Action is on 4. Sorry, as a constant. That is e to the power x, 1 all over. This is 1 plus 2 plus 1, that is over 4. The action is what is on 4. And when you look at that thing, that whole thing give us 1. So the answer is e to the power x. And finally, what is your solution? Your solution here is going to be equals to general solution is y is ycf plus ypi. That means that, so your y is given by ycf. If I remember, where it's a plus bx plus e small e minus x plus fx e to the power minus x plus what? Plus e to the power x. If you like, you can write it as that, a plus bx, that is common there, plus e to the power minus x, e plus what? Plus fx plus what? Plus e to the power x. That will be the solution. Wonder what is this? We erase that. Right, that is that, good people. That takes us to the end of solving differential equation using operator D. What is happening to my thing now? Right. It has just disappeared. Good people, are you there?
Yes.
Okay, sure. Now, that concludes that chapter. I wonder what happened to that problem. So our new chapter now, our last chapter for Maths 2 is the chapter which is called Laplace Transform. Laplace Transform. Laplace transforms. Okay. This chapter here is this chapter that will help us to solve again differential equation. But this time around, we'll use what is called Laplace transform. What is that? Definition. Definition. We define definition. Let f at t be a function such that t is bigger than 0. Then the Laplace of f at t denoted by L f at t. This is my capital letter L. So let f at t be some function with t bigger than 0. Just consider that t as your time. Then the Laplace of f at t denoted by Laplace f at t is given by, is defined by the Laplace of f at t is equals to the integral from naught to infinity of a to the power minus s of t times f at t what dt. In other words, the Laplace of f at t, is defined by this integral here. This type of an integral is called an improper integral. It's an improper integral. Now, you can see that in order for us to find the Laplace of a function, we simply multiply by this e to the power minus s of t. So, Laplace of f at t is given in terms of what? Of s, because of that s there. So when we are asked to find the Laplace of f at t, your answer will be in terms of s, because this e to the power minus s of t is the one that multiplies what? The given function f at t. Now, in other words, for us to find f at t, we must integrate that. But this integral is an improper integral. And we are not at this level expected to integrate an improper integral. Instead, we redefined that as follows. Redefined equals to, we redefine as the integral from naught to b of what? Of e to the power minus s of t f at t dt. We take the limit as what? As b goes to infinity. Instead of integrating with the upper limit as infinity, we don't do that. We'll simply say we take the limit as b goes to infinity of the integral from naught to b e to the power minus s of t times what? Times f at t d dt. Now, this definition are called definition from S. Right. So in other words, what does this tell us that? For us to find the Laplace of any function, we define that, we integrate it. Please, can you just unmute there? An example. Examples. You can be asked to find the Laplace of A, where A is a constant. Find the Laplace of A. A is a function, but in this case, it's a constant. Solution. So the Laplace of A, according to the definition, this definition now, because this one, of course, perhaps we can start off by saying from naught to infinity, that is what A times a to the power minus s of t dt. That is the definition of Laplace. But now we are not going to be able to integrate this integral because it's improper. We'll say we take the limit as what? As b tends to infinity of the integral from naught to b, a times a to the power minus s of t dt. That is how it is defined. Next, let us see whether we can integrate that. So the Laplace of a will be equals to the limit as b tends to infinity of, do you see that a is a constant? I can take it out of the integral sign, times a integral naught of b a to the power minus s of t dt. That becomes, I can even take this a in front there, a times the limit as b goes to infinity from naught to b of a minus s of t dt. Next will be the Laplace of a is equals to A times. Now it's a matter of integrating that, but I still have my limits there, goes to infinity into. Can I integrate that? E to the power minus S of st with respect to t. How do I integrate an exponential function? That is maths 1. So that will be minus E minus st over what? Over S. Then boundaries 0 to what? To b. Right? That gives us, it's A times limit as b goes to infinity. I think you recall, these are called upper and lower limits. How to work it out? It's minus A minus S of b. You start with b there, all over S, minus into minus A minus S of naught, all over what? All over S. Close that. That becomes A times the lim as b goes to infinity of, this is minus A minus SB over what? Over S plus, this will be 1, that will be 1 over S. Now, as b goes to infinity, if something goes to infinity, in other words here, b approaches infinity, very large, positive infinity. B can be 10, B can be 100, 1,000, a million. But now, if I put that here, A to the power minus S, say B was, say, 100 or 1,000, this can be written as 1 over A to the power 1,000 S. This number here becomes very small. So you may as well say it approaches 0, because as you increase B, but this is a fraction here because of that negative there. So this will be naught. So we'll get A only where there is B. As B goes to infinity, that's not there. There is no B there. That's 1 over S. Then your answer here is A times that is A times 0 plus what? A over S. Then your answer here is what? It's A over S, which means the Laplace of A, where A is a constant, is nothing else but it's a constant over S. You can see that Laplace, I said earlier on, the Laplace of a function will always be a number in terms of S, will always be in terms of S. So we have seen it here that the Laplace of a constant, therefore, the Laplace of this A, where that A was a constant, is nothing else but it's a constant over what? Over S. So using first principles, we can show that. In other words, if I say to you, what is the Laplace of 2? 2 is a constant. So what is that? According to that, it is 2 over S. What is the Laplace of K? K is a constant. K is a constant. K is a constant. It's constant over S. What will be the Laplace of minus 1? Minus 1 is a constant. It's minus 1 over S, etc., etc. We can arrive at these answers here using exactly what I have done above. So in other words, in a test or in an exam, or in a test, in this case, I can say, find the Laplace using first principles. If I've said using first principles, you use this definition here. You use this definition here. Let us see whether we can find the Laplace of something else. As example 2. Example 2, find the Laplace of what? Of S. Sorry, not S, sorry. Find the Laplace of T. Now, from now onwards, good people, instead of using S, X, we'll be using T. So we are then asked to find the Laplace of T from first principles. From first principles. Laplace of t. Solution, how do you go about Laplace of t? You use definition. Is nothing else but it is the integral from naught to infinity of t times what? A to the power minus s of t dt. This term, good people, is called, we say it has got a damping effect. A to the power minus s of t is a damping factor. Your lecturer in your electrical engineering will talk about this factor here, whereby you'll talk of a system that is critically damped. Is a result of that. Some systems are over damped. Others are what? Are under damped. So the damping effect is in most cases caused by that a to the power minus s of t. So when you are asked to find the Laplace of any function, you multiply by that factor, the e to the power minus s of t. But now we don't integrate that because it's far up beyond the scope of our course. Instead, you redefine that. You say is the limit as b tends to infinity of the integral from naught to b of the same function t e minus s of t what dt. Right? Next, Laplace of t, that will be equals to, now is a matter of integrating that. It's a matter of integrating that product. Can we integrate that again, maths 1, by parts, use parts? What do we say? We say let u be t, and then du, dv, sorry, be what? E minus st dt. Derivative of du with respect to t, du is dt. Then integrate the dv part to get v. V is minus e minus s of t over what? Over s. Integration by parts. Remember the formula for integration by parts. Remember the formula is what? It's u dv is u v minus integral v du. Therefore, the Laplace of t is equals to the limit as b goes to infinity of, I apply that here, u is t, and v is what? It's minus a minus s of t over s minus integral v, it's minus a minus s of t over s du is what? It's dt. If you work this thing out, that becomes the limit as what? As b tends to infinity of minus t e minus s of t over s plus integral, that's 1 over s. This s will come out as a constant, e minus s of t what? dt. Next, we integrate once more. You integrate once more there, that will be the limit as what? As b goes to infinity of minus t e minus s of t over s. If I integrate that once more, I'll get 1 over s coming out with a negative in front. So it's minus what? E minus s of t, s and s, that will be s squared, boundaries not to be. Right? It's a matter of applying the limits now. The upper and lower limits before I take the limit outside. Lim as b tends to infinity of, I apply b first. There is t replacing b. So that is minus b e minus s of b all over s minus e minus s of b all over s squared. Then I'm going to use 0 now, minus. Now if I put 0 here, that whole thing will be 0. Minus 0, if I put 0 there, that will be not. Minus, if I put 0 here, it would be 1 there. It's minus 1 over s squared, small bracket, close bracket. Don't forget here, I have the limit of what? Of t. That gives me, let me take the limit as b tends to infinity. Where there is b, there is b, there is b. And same story as before. When this thing goes to infinity, this will be naught. And again, that will be naught by the same reasoning. It's a to the power minus sb will be 0 if what? If b tends to what? To infinity. So in other words, that will be naught, limit is there, that will be naught, that and that, minus naught, minus plus. There's no b here. So this is not affected by b. And there is no b here. So this is minus, it's plus 1 over s squared. Therefore, the Laplace of t is nothing else but 1 over s squared. That is the Laplace of t. So far, so good. Are you okay there? I hope you are okay. You can also find the Laplace of this function. 3. The Laplace of e to the power what? T. You can also find the Laplace of that from first principle. You are lucky, good people, because you are not going to write any exam. In an exam, a question like this will always be there. And when you write a test, your test will be multiple choice question type.
So this thing is going to be on test 2, sir.
So the Laplace of e to the power t.
That's all.
Again, use definition. Laplace of e to the power t.
Huh?
Is the integral from naught to infinity. You take this function, e to the power t, and you multiply by e to the power minus s of t, what dt, by definition. Always, when you are to find the Laplace of any function, you multiply by that factor there. Then, but now, the bases are the same here. Bases are the same here. Add the indices. So indices, when you add them, is what? It is t, and t will be a common factor. It's going to be what? It's going to be minus s of t plus what? Plus t what dt. I'll write it in a more special manner. There is minus st. I'm taking out minus t out. So I'll get here integral naught to infinity minus what? Minus t into what? Into s minus 1. If I'm taking minus t out. Because my damping factor here had a minus outside. Well, I want to write it in that fashion. What dt? But this, I won't be able to integrate that. I won't be able to integrate that. But instead, I will take what? The limit. I might have as well put it here, it doesn't matter. As b tends to infinity of what? Of the integral of naught of b of e minus t of s minus that what? dt. Right. Sorry. Okay, fine. Right. Then can I then integrate that? If I were to find the integral of that, will be the limit as b tends to infinity of minus e minus t of s minus 1 all over s minus 1, what? From naught to b, if I integrate that. Then apply the upper and lower limit is the limit as b tends to infinity of minus e minus b of s minus 1 all over what? All over s minus 1 minus plus, because that one is already minus. Now you know the story now. Now this t now it's 0. Everything will be 0. Any number to the 0 power it's 1 over s minus 1. Now, as b tends to infinity, the same reasoning as before, this whole thing will be 0 plus what? 1 over s minus 1, which is nothing else but 1 over s minus 1. Therefore, the Laplace of e to the power t is nothing else but is 1 over s minus 1. We can find Laplace of different functions of my choice or of the functions given in the book. In our notes, good people, on page 20. The notes that I gave you, those that they did not get the study notes, they are there next into my office there. You can go and pick them up. Now, on page 20. Page 20. We have a table. There's a table of Laplace transform. There's that table there, which will always be given in a test or in an exam. There's a table of Laplace transform. I'm going to use it now in case you do have it there. Take it out there. Take your notes, the white notes that I gave you, and we'll go through a few of those. Now, we have a function together with the Laplace. In other words, standard Laplace transform, whereby different functions are given. Some of them, we've proved them. One of them is this one, f at t, the Laplace of what? Of t to the power naught. T to the power naught is nothing else. What is t to the power naught? It's a constant, it's 1. And the table says there, the Laplace of that is nothing else but what? It's 1 over s. We've proved that. We've proved that. This is given as t to the power naught there. Next one is the Laplace of t to the power n. What we have shown here is t to the power 1, but the formula says here it is n factorial over what? Over s n plus 1. That is the Laplace of t to the power n. In our case, if n, in our case, n was 1 here, the one that I did, Laplace of t, that is Laplace of t. Therefore, n is 1 here, so the Laplace of t, we've seen it though, it's 1 factorial over, because n is 1 there. It's 1 there. All over s to the power 1 plus 1. 1 factorial, it's 1, that's 1 over what? Over s squared. And we've proved that the Laplace of t is 1 over s squared. We can even find the Laplace of t cubed, of t squared, or t cubed. The Laplace of t squared. According to this formula here, the formula says n factorial, my n is 2. Is 2 factorial over what? Over s to the power 2 plus 1. And 2 factorial, it's 2 over what? Over s cubed. So the Laplace of t squared is what? Is 2 over s is 2 over s cubed. We can show it by using first principle, but we have a table, we have a formula. Laplace of what? Of t to the power 7 would be what? Would be 7 factorial over what? Over s to the power 8. And 7 factorial, you can work it out, etc., 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 etc. So that table there will directly give us the Laplace of a function without going through what? The first principle to find it. So next is the Laplace. Is the Laplace of sine at. We can show it from first principles. We can show it using definition. A to the power minus what? Minus s of t times what? Times sine at dt. We can show it, but the table provides us an answer immediately. The answer here, the Laplace of sine at, according to that, it is a over what? Over s squared plus what? Plus a squared. That is the Laplace of sine at. That is, example, if I say, what is the Laplace of t, of sine t? Laplace of sine t, using that, there is my a here. In other words, the coefficient here is 1. So it's 1 over what? Over s squared plus what? Plus 1 squared, which is just 1 over sine squared. What about the Laplace? The Laplace of sine 4t. The Laplace of sine 4t, according to that, is what? It's 4 over what? Over s squared plus what? Plus 16. The Laplace of what? Of sine 10t is what? It's 10 over s squared plus 100. We can show that using first principle, but the table is there as a quick tool to give us the correct answer. And again, further down there, we have the Laplace of cos 80. The Laplace of cos 80 is given by s over s squared plus a squared. From tomorrow onwards, good people, when I have a lecture with you on Laplace, you must always bring your table of Laplace transform. In other words, the white notes that I gave you, so that you'll always refer. So the Laplace of cos 80 is s over s squared plus a squared. We can show it from first principle, but the table is there for us to give us a quick answer. So if you are asked to find the Laplace of cos t, Laplace of cos t is s over what? Over s squared plus 1. That of Laplace of cos 40 will be what? Will be s over s squared plus what? Plus 16. Jalo, jalo, jalo. We can even find the Laplace on the table there, etc., etc. Many functions with different Laplace. So the Laplace of what? Of e to the power bt is given as, we have proved it, as 1 over s minus b. Later on, we'll talk about this and we'll say it's a what? It's a shifting property. We'll talk about that. Why? Because that b here, s has shifted by b units to the right here because this was positive. So if I say to you, what is the Laplace? What is the Laplace of e to the power 2t? Is what? It's 1 over s minus 2. Similarly, what will be the Laplace of e to the power minus 2t? This is going to be 1 over s plus what? Plus 2. Note the difference. It's e to the power positive 2t. It shifts by s by 2 units to the right. If it's negative 2, it shifts by 2 units what? To the left of s. Jalo, jalo, jalo. That table is on page 20, page 20, page 21. Jalo, jalo, jalo. Let us play around with such and see whether we can find out something. Find, use tables to evaluate the following. 1, the Laplace of cos 3t minus sine 3t plus what? Plus t squared. Let us use table to evaluate that. Then we start. Mind you, if I want to evaluate that, this can be written as Laplace of that. I can say it's a Laplace of cos 3t. Laplace of the whole lot, I can find the Laplace of each and every term, minus the Laplace of sine 3t plus the Laplace of what? Of t squared. That gives us. Do I know the Laplace of cos 3t? Yes. Cos is what? Is s over s squared plus 3 squared. That will be 9 minus the Laplace of sine. Sine is a constant. It's 3 over what? Over s squared plus 9 plus Laplace of t squared. Remember, t squared, it's n factorial over s to the power n plus 1. So it's going to be 2 factorial over what? Over s to the power 3. That becomes, well, I can add like terms here. Bases are the same, not bases, denominators. S squared plus 9. That becomes s minus 3 plus what? 2 factorial. It's a 2 over what? Over s cubed. Bring that over the same LCD. Over the same LCD, that becomes what? Everything is s cubed into s squared plus 9. that into that will be s cubed into s minus 3 plus what? Plus 2 into what? Into s squared plus what? Plus 9. That gives us s to the power 4 minus 3s cubed plus what? Plus 2s squared plus what? Plus 18. It looked like we can't do anything there. All over what? S cubed into s squared plus what? Plus 9. And you leave it there. You can't further simplify that. So we are just using tables. Next. 2. So find the Laplace of cos 3t minus e to the power minus 2t plus or minus or plus whatever. I'm just creating my own problems. I don't have them here in front of me, but I'm just taking them at random. Minus Laplace minus what? Minus sine 5t. And we find the Laplace of cos 3t. You page through Laplace of cos 3t. According to my table here, it is given as cos. It is s over s squared minus what? Minus 3 squared. That will be 9. Therefore, Laplace, if you like, you can take the Laplace of the individual terms, or you just put the Laplace of each and every function inside. So the Laplace of that, it is s over s squared minus 9 minus Laplace of e to the power minus 2t. It's 1 over s plus 2 plus the Laplace of sine 5t is what? It is 5 over what? Over s squared plus 25. If you are able to bring those over the same LCD, you can do that and simplify where possible. 3. You can be asked to find the Laplace of cos what? Of cos what? Bracket all squared. Now, we don't have the Laplace of that. We don't have the Laplace of that. We don't have the Laplace of cos squared. But we remember something. What is that? We recall that cos 2t was equal to what? Was equal to cos squared t minus sine squared t. Then I need to find that. I need to change that. That gives me cos squared t minus sine, it's 1, minus cos squared t again. That gives this and that. That will be plus, they'll get 2 cos squared t minus 1. That gives me what? Cos 2t. Then make cos squared t the subject of the formula, because that is what you are going to replace with here. Therefore, cos 2t plus 1 is what? Is 2 cos squared t. Therefore, cos squared t is half of what? Of 1 plus what? Plus cos 2t. Therefore, hence, therefore, the Laplace of what we're given, which was that? Cos squared. Now I'm replacing that now. By what? By half into 1 plus what? Plus cos 2t. But half is out there. Take it out of the Laplace. So it's 1 over 2 Laplace of 1 plus what? Cos 2t. Then half. Then I can take the Laplace of the individual terms. What is the Laplace of 1? 1 is a constant here. It's 1 over s. 1 over s plus. What is the Laplace of cos 2t? The Laplace of cos is s over s squared plus what? Plus 4. If you like, bring that over the same LCD. That's s into s squared plus 4. That will be s squared plus 4 plus what? Plus s squared. So your answer here is half into what? 2s squared plus 4 all over what? All over s into s squared plus 4. And when you simplify that, take out 2 as a common factor there, then the half and the 2 will cancel, then you're left with s squared plus what? Plus 2 over s into s squared plus 4. That's that. You may as well be asked to find the Laplace of cos t minus sin t, say all squared. Laplace of that. Now, to find that Laplace, first of all, work it out. Is the Laplace of cos t minus sin t. You square the first term is cos squared t minus twice cos t sin t plus what? Plus sin t squared. That gives us. Now, if you look at cos t squared sin t squared, that is 1. It's an identity. So it's 1 minus 2 cos t sin t. But again, this is an identity. We call what? Sin 2 theta was what? 2 sin theta cos theta. So that is exactly that. So that is the Laplace of 1 minus what? Minus sin 2t. Can I find the Laplace now? Yes. Laplace of 1 is 1 over s. Laplace of sin is going to be 2 over what? Over s squared plus 4. Bring that over the same LCD. That becomes that is s into s squared plus 4. That is s squared plus 4 minus what? Minus 2s. That is your answer. Etc., 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 etc. You can find the Laplace of different functions. So long as you have a table of Laplace next to you, you can always find the Laplace of that particular function. Let me see whether I have the last example. I seem not to have at this point in time. So what is it that we know now, good people? Now, summary. Summary is that we define the Laplace of f at t as nothing else but the integral. The integral from 0 to infinity of e to the power minus s of t times f at t, what dt. But that integral is not easy for us to integrate. Instead, we take the limit as b tends to infinity of the integral from 0 to b of e minus s of t times what? F at t, what dt. That is what we did. That is from first principles. Then I did show you some Laplace from first principles. Laplace, that was the Laplace of t. From what? From first principles, and many more. And then what we did next, instead of using first principles, we have a table of Laplace transform. Table of Laplace what? Transforms. And this is on page 20 to what? To page 21 in your study notes. So basically, this is what we have done today. And this is very important going forward. So as a precautionary measure, good people, I would like you to go to your notes again on page 20. You go through those Laplace transform functions given there. Then you play around with them. You find your own function given the Laplace of the function given there. Then you work it out. Play around with it until you know what is actually happening there. Those that perhaps you don't know, leave them. We'll talk about them when we meet again. When? Tomorrow. So tomorrow again at 5:30, we are going to have the same lecture at 5:30, but we'll continue from where I've just ended today. What we have done today is very important, is that fortunately, because your test will be on multiple choice, so I won't ask you to find the Laplace using first principles, but I will always refer you to the table to find the Laplace of some function. Thank you very much, good people. Let me just stop here for today. Thank you. Okay.
Thank you, sir.
Yes, our next meeting is at 5:30 tomorrow.
Sir,
Yes.
izophuma ama-Laplace ku-test 2.
No. Sorry. Your test 2 will be operator D, from the theorems up until we solve differential equation, everything. That will be for test 2. Laplace will be test 3.
Okay, sir, ngiyabonga.
Okay, thank you very much. Tomorrow 5:30. Okay, thank you.
Hayibo.